Hello! In a previous video, I asked and answered the question, if we take the second order elements of some non-standard model of weak S1s and just looked at their omega parts, looked at their intersections with the natural numbers. This is going to give us a collection of subsets of the natural numbers, one subset for every second order element. And the question is, what collections of subsets of the natural numbers can we get in this way? And the answer was, as long as our collection is closed under the things that the axioms require it to be closed under, we can make any collection of subsets work. But this isn't quite the question we're interested in answering. Because of our cut and paste construction, the thing that we're really interested in is looking at infinite cuts and looking at possible tailhead functions over those cuts. The construction we did in that previous video didn't tell us anything about the shape of that cut. Was it something like the cut between omega and z in omega plus z, or was it something more complicated? And we could modify our model existence theorem construction to require that the first order part be omega plus something very dense. One copy of z for every rational number, for instance. But what about the most basic type of infinite cut, the cut between omega and z in omega plus z? What sorts of tailhead functions could we expect for those sorts of cuts? And the construction that we did in that previous video doesn't tell us anything about that. In this video, I'll show you how we can partially answer the question, if we have an omega plus z model of weak S1s, what could the intersection of its second order elements with the natural numbers look like? Our argument in that previous video was a standard use of the compactness/model existence theorem. We started off with our base structure, weak S1s, and we added some new constant symbols. These constant symbols, our goal is to have them represent non-standard elements. So we start off with the collection of true formulas about weak S1s. We call this the theory of weak S1s. Model theorists use the word theory to refer to a consistent collection of formulas. And we add on a bunch of new formulas specifying the properties that we want these constants to satisfy, that we want the non-standard elements that we're adding on to satisfy. When we chose the properties that we wanted these new constant elements to satisfy, we wanted it to be the case that every finite subset of them was consistent with our original theory. And in fact, for every finite subset of them, we could find an element of our original structure that satisfied that finite set of properties. But we wanted it to be the case that there was no element in our original structure that satisfied the infinite collection of properties, therefore requiring this constant symbol to refer to a new non-standard element. These sorts of collections are things that model theorists talk about all of the time, and so they give them the name type. We need to be a little bit careful. I've been talking about two-typed theories, for instance. That's a slightly different notion of the word type. And of course, there's also something called type theory, and this has nothing to do with that. It's useful to be able to talk about how many elements our types are talking about. So we call them n-types. This is going to refer to a collection of formulas about n elements, and any finite subset of which is going to be consistent with our original theory. And of course, if any finite subset of them is consistent with the original theory, then the entire collection is consistent with the original theory, because to prove a contradiction, you only need finitely many hypotheses. Typically n is 1, and it's useful to also look at when n is finite, and I've also seen cases where n is infinite, although those seem to be less common. In this video, there are two separate types that I want to focus on. When we wanted to add a new second-order element to our models of weak S1s that had a particular intersection with omega, we did this by looking at this particular type here. Given a particular subset of the natural numbers w, we introduced a new constant symbol, c sub w, and we specified some properties that we wanted this new constant symbol to satisfy. So this here is a second-order 1 type. It's a one type because it's referring to one new element, and it's second order because that new element is a second order element. One can, of course, have types that refer exclusively to first order elements, or some sort of mixture of first and second order elements, although we won't see that later case in this video. And the formulas that we wanted to add on describing this constant symbol were what we expect. The nth successor of 0 is in this set here if n is in our set W, and the nth successor of 0 is not in this set here if n is not in W. And so together, this collection of formulas, when we construct a non-standard model that has an element given by this constant symbol here, it requires that element to contain exactly the natural numbers that we'd like it to contain, exactly those in the set W. And of course, if W is infinite, it's going to contain some non-standard first-order elements as well, but we don't worry about that. Each subset of the natural numbers W gives us a slightly different type, a slightly different collection of formulas describing our constant symbol. And our goal for this video is to construct an omega plus z model of weak S1s that manifests a bunch of these types. The other type that we're going to want to talk about in this video is a first-order 2 type. We're going to have two constant symbols / variables, e and f, and we're going to want to specify that e is larger than the nth successor of 0 for every n, so we're going to have a separate formula for every n specifying that e is larger than the successor n of 0. And we also want to specify that f is larger than the nth successor of e. Together, this infinite collection of formulas requires that e and f both be infinite, and that f be infinitely larger than e. As usual, because every finite subset of this collection of formulas is satisfied within the original weak S1s by an appropriate choice of constants e and f, we can apply a model existence theorem construction to construct a model that has two elements, e and f, that satisfy this type. But that's actually the opposite of what we want. Having two elements that are infinite and infinitely far away from each other requires us to have at least two z parts within our woozle. Any model that manifests this type here has to be at least omega plus z, and might wind up having way more z parts. We want the opposite of that. We want a model that doesn't have two infinite elements that are infinitely far apart from each other. In other words, we want an omega plus z model. If we have a model of weak S1s that doesn't manifest this type, that is to say, it omits this type, then it's either going to be an omega plus z model, or it's going to be the standard model. So our goal is to manifest a bunch of these types here for various w's, while omitting this type here. I should note that model theorists are typically interested in complete types, that is, collections of formulas about some elements that can't be enlarged anymore without introducing some sort of inconsistency. That is, for any formula, either that formula or its negation is in the collection. In a sense, the thing that we're doing is fully specifying the properties of our elements, and this is a really interesting thing to look at. What is everything we can say about two first-order elements within a model of weak S1s? Well, it's more than just this. Remember that we can specify the modular congruences of elements using the language of weak S1s as well, and we haven't bothered to do that. That's because I'm only using types with the idea of either manifesting or omitting those types, and in that case we really only care about partial types. We don't need to fully specify the properties of an element in order to either manifest it or to omit it. Now, the model existence theorem is incredibly powerful. It allows us to manifest a whole bunch of types at the same time. We were able to manifest types of this type for every subset of the natural numbers simultaneously within a non-standard model of weak S1s. The problem with the model existence theorem is that it allows us to say we would like these types to be manifested within our structure, but the models that we wind up getting might manifest types that we didn't ask for and don't need. Of course, if we manifest a particular C sub W for some particular subset of the natural numbers, we're going to have to close under Boolean operations and runs of automata, so having one element like this in our non-standard model is going to force a number of other elements to be in our non-standard model as well. But the model existence theorem might hand us a bunch more that we don't need. And we have no way of preventing that other than going into the proof of the model existence theorem and being more careful about what the construction actually tells us. So again, we're going to need a different tool. We're going to need the omitting types theorem. Now, the omitting types theorem is particular about what types of types we can omit. If we have a type that winds up being equivalent to a single formula, then whether or not there exists an x1 through xn satisfying this type tends to already be decided by the original theory. For instance, if we let our theory T be the set of true formulas of our standard model of weak S1S, then for a particular phi, either this formula is going to be true of that standard model, or its negation is going to be true for that standard model. In the first case, this type here has to be manifested in all non-standard models of weak S1S, and in the second case, in none of them. It's really only when we start talking about infinite collections of formulas that we can have some models that manifest them and some models that don't. But of course, this sort of situation doesn't just happen when our type consists of one formula. It can also happen when our type acts like it consists of one formula. We say that a type is isolated if there's some formula phi such that any tuple satisfying the formula satisfies the type. And we can't cheat here, phi has to be satisfiable. Right, you could imagine cheating and having a formula that's always false, and then anything that satisfies that formula satisfies the type vacuously. Just like the term compactness, the term isolated comes from topology. There's a way of applying topological perspectives to model theory, and if you're interested in that, I encourage you to look into what are called stone spaces. This isn't quite what I said before. We're not finding a formula phi that's equivalent to the type, but rather acts as kind of an upper bound on the type. But in the case of complete types, these are equivalent. A complete type is isolated if and only if it's equivalent to some single formula. And that means that there's something genuinely infinite about our non-isolated types. As a simple example, suppose we're looking at the type of all formulas over the language of weak S1S that are true of the number 2. This may be an infinite collection of formulas, but it can be captured entirely by the single formula x is equal to the successor of 0. This formula here isolates this type, so this is an isolated type. This is a first order 1 type because it's this formula here takes in only one first order element. And this type here is complete because any formula is either true or its negation is true of 2. So we can't toss in any more formulas into this collection without having both a formula and its negation in the collection, thus having a contradiction. On the other hand, the collection of formulas that say that x is greater than n for every natural number n, this type here, this is an incomplete type. Again, over weak S1S, we can specify the modular remainders of x. And there's also a bunch of formulas that are like consequences of this that we can toss into this collection as well. It's not a full collection. And this is also a non-isolated type. There isn't a single formula in X that implies all of these formulas in this collection. The omitting types theorem says that while the question of manifesting or not manifesting isolated types tends to already be answered, in the case of non-isolated types, when the circumstances are right, we can omit those types. And of course, you could use a model existence theorem to manifest those types. Unfortunately, the omitting types theorem isn't quite as flexible as the model existence theorem. It needs to be the case that we're working over a countable language, because in the proof of the omitting types theorem, we're going to be explicitly constructing our model using some sort of countable construction. At every stage, we're going to be introducing new elements to our structure and deciding on their properties, and we need there to only be countably many stages in order for this to work out right. As a bonus, though, We know that the resulting model has to be countable, because if we've only added in finitely many elements at each stage, and there have only been countably many stages, as a result the structure is going to be countable. An intuition that I found very helpful about the difference between isolated and non-isolated types in terms of our ability to do this construction is that for isolated types, we need to make sure that every single tuple of our model doesn't satisfy this very specific formula. And so as our proof is going along constructing our model, at some point we might decide whether or not a particular tuple satisfies this particular formula phi. And we might decide that it does, and so we have to kind of like backtrack, by backtracking we might make another tuple satisfy the formula phi. And then when we backtrack that, we might make another tuple satisfy the formula phi, and so on and so forth. And indeed, if our original theory says that there exists some tuple that satisfies the formula phi, we're going to be stuck backtracking forever. On the other hand, non-isolated types are genuinely infinite. As we're working through this construction, we get to some stage where we decide we want to make sure that this tuple here doesn't satisfy this type p. And it's not going to matter which formulas we've already decided are true of our tuple, as long as there's only finitely many that we've already decided so far. Because our type is genuinely infinite, there's going to be a formula in our type that we haven't decided about yet. And we just say that our tuple doesn't satisfy that formula. And that will make sure that that particular tuple doesn't satisfy all of the formulas in the type, and we just do that for every tuple. If we're careful about how we do this, we can make sure that every single tuple doesn't wind up satisfying p. Now, of course, you might ask, where does the omitting types theorem tell us anything about manifesting types? Remember that our goal for this video is to construct a non-standard model of weak S1S that manifests a bunch of different types and omits one. Well, it happens in the same way that it does for the model existence theorem. We introduce a bunch of new constants and throw them into our language, and then we add on a bunch of formulas describing the properties that we want those constants to satisfy. Now there's a tricky bit here. We want to add on a constant symbol for every subset of the natural numbers to the language of weak S1S, and add on a bunch of formulas to t, specifying what natural numbers should be in the second order element given by that constant symbol. The problem is, we would be introducing uncountably many constant symbols to our language. And the omitting types theorem, in some sense, genuinely requires that we're working over a countable language. So we have to give up hope of manifesting uncountably many subsets of the natural numbers. We have to just pick some countable collection of subsets of the natural numbers and just manifest those. And I'm going to assume that all of these subsets are infinite because the finite subsets are already there. In the standard model and in any non-standard model, we already have arbitrary finite subsets of the natural numbers. So first we're going to add on all of this stuff to our language and our theory, and then we're going to show So our goal is to show that this first order 2 type, specifying that there are two infinite elements that are infinitely far away from each other, is not isolated over this augmented theory. It's really important to remember to show that your type that you're trying to omit is not isolated over not just the base theory, but the augmented theory. For instance, the first order 1 type specifying that there's an element that's non-standard is not isolated over the original weak S1S theory. However, when we augment the theory with all of this stuff, it becomes isolated. If we're trying to manifest a single CW, where W is an infinite subset of the natural numbers, that's going to require us to be looking at a non-standard model of weak S1S. And so it's going to have non-standard first-order elements in it. Manifesting even one of these types requires us to manifest this type here. And what we've done is, by augmenting our original theory with all of this new stuff, we've actually turned this type from being non-isolated into being isolated. It's isolated by the formula specifying that x is an upper bound on CW given a particular W. We've introduced this new constant symbol into the language so we can talk about it. And this formula isn't fundamentally false because every second order element has an upper bound. So again, we need to show that this type here is non-isolated, not just over the original weak S1s, but also over this augmented weak S1s. Once we've done that, we'll have shown that there's a non-standard model of weak S1s that manifests this countable collection of CWs, but omits this type here, and thus is an omega, well, it can't be an omega model, so it has to be an omega plus z model. So we'll have an omega plus z model that manifests these countably many CWs. And unfortunately, that's as good as I've gotten. I'm not sure what happens in the uncountable case. So our goal here is to prove that this particular type is not isolated, and in order to do that, we will assume that it is isolated and prove a contradiction. For shorthand, I'm going to refer to this type as 0 is infinitely less than E is infinitely less than F. This tells us two things. By the definition of isolating a type, it means that any pair E and F that satisfies this formula necessarily satisfies this type. Not just in a specific model, but in every model of our augmented theory. We've come up with a single formula that always captures this phenomenon here. And again, this implication can't be vacuously true. It has to be the case that there is at least some model, maybe not all models, but there has to be at least some model in which phi is actually true of some pair of elements. So let's take a look at that model where phi is satisfied. We're going to be able to find two elements, A and B, such that phi of A comma B. In some model, we're not really sure what the first order type looks like, and so I've drawn it like this, but you shouldn't be thinking of this as omega plus z. There might be lots of stuff going on in this range here or in this range here that I just haven't drawn. I've only drawn the relevant stuff, the starting out, the bit containing A and the bit containing B. And of course, because phi holds of A and B, it necessarily needs to be the case that A and B are both infinite and infinitely far apart from each other. One of the key proof techniques in weak S1s is the ability to turn any formula into a finite state automaton, into its canonical form. But that's not quite true over our augmented theory. We've added new things into the language that aren't covered by finite state automata. Specifically, we've added these new CW constant symbols. But luckily, we can view this formula here as a weak S1s formula that has references to E and F, these two variables here, and then also refers to some finite number of the CWs. And so if we change the way that we think about those CWs from being an inherent part of the language, an inherent part of the formula, to being inputs to the formula, then we can turn phi into a finite state automaton. And we don't know much about these CWs. We know what they start with in their omega parts, right? We've required that these sets here agree with W. W is some subset of the natural numbers, and we've required these sets here to agree with them on the natural numbers, but we have very little control over what's going on in the non-standard part. Now, there's several cases here, and you kind of have to handle them separately, but I'll just talk about the most interesting case, which is where the CWs extend beyond, at least some of them, extend beyond B. And so when we try to run a finite state automaton with this input here, it's going to stop after reading the last character somewhere over here. So we're going to translate phi into some finite state automaton, and that finite state automaton is going to have some sort of run when we run it on this input. Remember that one of the facts about weak S1S is that we can run automata on whatever inputs we want, and they'll behave correctly even if those inputs are infinitely long. And when we talk about running finite automata, what we're really talking about is having some sort of partition of the set from 0 up to 1 plus the largest input character that satisfies a particular transition relation. So if I wanted to be explicit about that, I could just have a separate row of our run for each element of that partition, each state separately, and just keep track of write a 1 in positions where we're in that particular state. But instead I'm going to combine all of that information into a single row of this table just so it doesn't get too large. And I'll write down which of the states we're in at each point. So again, after reading the last non-zero input, we're going to transition into the final state, and this should be an accept state because phi, the formula corresponding to this automaton, is true when we input these things. And again, the run of this automaton has to satisfy the transition function. If we're in a particular state and we see a particular input, we have to go into a particular state, according to however the translation of this formula into an automaton works. So the overall idea of this proof is that I'm going to want to cut and paste this region here between A and B. I'm going to want to cut this out and replace it by only finitely many positions. And we can do that with a standard cut and paste argument, just by kind of moving where we cut just a little bit after A, and then we have the finitely many positions that we're interested in here, and we just change those in each of these elements as necessary. So I'm going to cut and paste here and replace this gap here where there might be lots of stuff. There might be lots of non-standard parts going on here. I want to replace this gap with a finite number of positions. The result will be a new model of weak S1S with a new A, a new B, new CWs, right? We're kind of cutting out this middle bit of the CWs. And then also we're cutting out this bit of the run. But when we do this gap removal operation, we're going to get a valid run of the original automaton. It's still going to satisfy the transition relation, and it's still going to have an accepting final state. And so that means that this formula will still be true of our new A and B. But in the new model we're constructing, A and B are only going to be a finite distance apart. And that's where our contradiction is going to come in. Because, again, we said that phi of AB, which is still true in this new model, implies that A and B are infinitely far apart from each other, which is not true in this new model that we're going to construct. So how are we going to do this? How are we going to find some finite number of steps that we can replace this infinite bit here with to still satisfy the transition relation? A and B refer to first order elements, so their representations in terms of sets should be singletons still, so we can't change the fact that these are all zeros. We can change the CWs around as we want. They'll still satisfy the properties that the CWs have to satisfy, as long as we don't modify them on this initial part here. And we can specify the run however we want, as long as it satisfies the transition relation. So let me show you how we can find an appropriate finite sequence of inputs and states to take us from A to B in a finite number of steps, in a way that still gives us an accepting run of the automaton. To do this, let's zoom in on this region here. So we know that if we start off in state R and we read this particular input here, it's going to take us into state S. Now what we're going to do is we're going to jump forward to the last time before B that the state S appears. And again, because there's infinitely much stuff going on between A and B, we might wind up having to jump forward infinitely many steps to get here. But we can definitely find a last point before B where the state S shows up. All we're looking for is the maximal element of the characteristic set for S, right? The set of positions where we're in state S, and the interval from 0 to b, both of which exist in this model of weak S1S, so we take their intersection, and by the axioms of weak S1S, there has to be a maximum element for that set. So we're going to the last appearance of S before B. And then at that point, we're going to read some input, and that's going to take us to another state. And then we're going to go forward again to the last position before B, where state T shows up. And that'll be potentially infinitely farther along. Maybe it's this T here that's the last instance of T. Who knows? It doesn't really matter. The important thing is that this is the last T in this run appearing before B. And then if we're in state T and we read what we read there, it's going to take us to another state. And eventually this process is going to finish. There's only finitely many states, and after we've reached the last S before B, we can never hope to see S again. So eventually we're going to use up all of the states that appear before B, and then we're done. We have to reach B at that point. And it turns out in this case, when we take this Q and travel forward to the last Q appearing before B, that's this Q here, and so we've reached B and we're done. And so in doing this search, we found a finite sequence of inputs that start off with 0, 0 that take us from this configuration here to this configuration here is a valid sequence of steps of our finite state automaton. So we can just squish that stuff together and insert that here. We know that if we're in state R and we read this input, it takes us to state S. If we're in state S and we read this input, it takes us to state T. If we're in state T and we read this input, it takes us to state Q. And if we're in state Q and we read this input, it takes us to state P. So this here is a valid accepting run of our automaton, the same automaton, same transition diagram. It's taking place in a completely different model of weak S1S. But again, we can do that. We just cut and paste two pieces of our original model. One that's everything before this position here, a few positions after A, and the piece of our original model that's everything at B and after. We cut and paste those together to create a new model where A and B are only finitely far apart from each other. We'll have new notions of CW1 through CWN in this model, which are pretty much just the same as they were originally, but cut and pasted, and with the appropriate configurations in between A and B, according to what we found to get the run to work out right. And of course, on the standard piece, on the omega piece, we haven't changed CW1 through CWN because we've only made changes after A, and A is non-standard itself. It's infinitely larger than 0. But this is the same automaton, and it accepts these new inputs. So this formula phi that we have is true in this new model of this A and this B. Unfortunately, in this new model, A and B are only finitely far apart from each other, but the fact that A and B satisfy phi should imply that they satisfy our type, that they're infinitely far from each other. So this is our contradiction. As such, we can conclude that this type here is non-isolated, even in our augmented theory where we've added these new constants, CW1 through CWN, that gives us a little bit more expressibility, that might give us the ability to talk about a formula that isolates a type that we might not originally have had in the original weak S1S. But adding these new constant symbols doesn't help us at all in this case. This type here is still non-isolated, and what that means is that we can omit it. Thus, the omitting types theorem gives us a model of our augmented theory, weak S1S, with these extra constants, CWs. We're going to have countably many CWs. Again, I don't know what happens in the case where we want uncountably many CWs. And because that model isolates this type here, it has to be an omega plus z model. Again, the only way to omit this particular type is either being an omega plus z model or being the standard model, and we can't have these CWs in the standard model. So we're definitely looking at an omega plus z model. So this is it. This is the last result in my thesis that I'd like to cover in this series. But this isn't the end for regular languages and model theory. In the next couple of months, I hope to produce some supplementary videos covering topics that I really should have covered but didn't get around to. I also hope to eventually start a video series on notions of finite state automata that take in as input things other than finite words. It turns out in some of these cases, the collection of things that are all equivalent to each other, equivalent expressions of regular languages, wind up being as robust as they do in the case of regular languages of finite words. So thanks for watching, and I hope that you'll join me for that. In the meantime, if you have any questions or comments, please leave them down below. And I hope to see you in a future video.